Let's investigate the research question, can dolphins communicate in an abstract way? This is a famous study from the 1960s in which Dr. Jarvis Bastian trained two dolphins named Buzz and Doris, each individually to respond to lights by pressing a button. If they saw a light come on and stay on, they needed to press the right-hand button to receive a food reward. If they saw the light come on and blink on and off, then they needed to press the left button to receive a reward. Then, Dr. Bastian tested the dolphins' ability to communicate by putting them into a pool with a curtain separating the two dolphins. Then he showed Doris a light, but only Buzz had access to the buttons. If Buzz pressed the correct button based on the light that Doris saw, then both dolphins received food. So the dolphins had to communicate to get the reward. What happened was that Buzz pressed the correct button 15 out of 16 times. So the question is this convincing evidence that Buzz's long-run proportion correct is greater than 50%? That is this convincing to make us believe that Buzz isn't just guessing, that Doris really is communicating to Buzz which button he should push? Here, the number 15 out of 16 is the statistic, the value from the sample that gives us information about our research question. And Buzz's long-run proportion correct is the parameter we're interested in studying. That is the numerical value about the long run or the population if we could have Buzz press the button infinitely many times and record data about all of them. Usually we don't know the exact value of the parameter, which is why we try to use the statistic to learn about it. We'll try to decide if 15 out of 16 is convincing evidence using the 3S strategy. We start by choosing a statistic to summarize the data. In this case, we could choose 15, the number of correct button pushes that Buzz made, or 15 out of 16, which is 93.75%. Next, we'll simulate a by chance alone explanation for the data. That is, if Buzz really were just guessing, what sort of results would we expect to get? Finally, we'll consider the strength of evidence. Is the observed statistic of 15 out of 16 unlikely to occur if the chance model is true? So what chance model should we use? Let's suppose that Buzz is just guessing. That is, that his long-run proportion of pressing the correct button is 50%. In that case, we want to know how unusual it would be to get 15 out of 16 correct. Well, we could simulate this by flipping 16 coins, where one coin flip represents one guess by Buzz. Heads can represent a correct guess and tails can represent an incorrect guess. Then one repetition of 16 coin flips represents one study of 16 guesses, and we can count how many heads we get to represent how many times we expect Buzz to press the correct button. Give this a try. Find a penny or a quarter in your pocket and try flipping it 16 times, and keep track of how many heads you get. Here are the results from 13 pairs of students, each flipping 16 coins in a previous semester. All of them had a number of heads between 5 and 11, averaging around 8, as you would expect. None of the pairs of students got a number of heads as high as 15 out of 16. So this suggests that Buzz getting 15 out of 16 button presses correct is pretty unusual if he were just guessing. We can get a more accurate sense of how unusual it is to get 15 out of 16 correct button pushes by doing more repetitions of 16 coin flips. But that could take a while, so let's have a computer do it for us. We can get to the one proportion applet by going to Canvas under General and then the Applets link.
Here I am at the Applets link. I'm going to click the one proportion applet, and then we can simulate flipping coins. We're going to leave the probability of heads at 0.5 because we want to simulate under the chance model where Buzz has a 50% chance of guessing correctly. But I'm going to change the number of tosses to 16. And then we'll click Draw Samples. We can watch the animation of the coins being flipped. And in this simulation, I got 7 heads and 9 tails. If we scroll down, we can see a graph showing 1 dot at the value of 7. So each dot here represents one set of 16 coin flips, and it's telling us the number of heads that we got. So now we can do more repetitions by increasing the number in the number of repetitions box. Let's do 1,000. Now our graph shows a distribution made up of a bunch of dots. They're so close together that now they just look like lines, showing that, as expected, the number of heads in a set of 16 coin flips tends to center around 8, and it ranged from 2 to 15. But it looks like something as extreme as 15 out of 16 is very unlikely. The number 15 is far in the tail of this distribution. Alternatively, we could switch this graph to show the proportion of heads by clicking on this radio button over here. So here we see that 15 out of 16, which is 0.93, is very far out in the tail. Changing to the proportion of heads just changed the labels on the horizontal axis here. It didn't change the heights of any of the bars.
Because 15 out of 16 heads was far in the tail of our by chance distribution, we say that this result is statistically significant. That is, that it's unlikely to occur by chance alone. This means that we can rule out random chance as a plausible, that is, believable, reason for getting 15 out of 16 correct. It's still possible that Buzz was just guessing, but he would have had to have been very lucky. This leaves us with several plausible explanations. It might be that Doris and Buzz really are communicating, which is what Dr. Bastian was trying to prove. Or it might be that there's a pattern to the correct answers that Buzz has figured out. For example, maybe Dr. Bastian accidentally fell into a pattern of left button, right button, left button, right button. So Buzz is getting the answers correct, not because he's communicating with Doris, but because he figured out the pattern. Or it might be that Buzz can see the light around the curtain, that there's a problem with the study. You may be able to come up with other plausible explanations for why Buzz's percentage correct in the long run is greater than 50%. Dr. Bastian's goal is to design further studies to try to eliminate all the plausible explanations other than the one he was trying to prove. Now it's your turn. In the Introduction to Chance Models activity, you and your group will use the one proportion applet to explore the statistical significance or lack thereof of a follow-up study that Dr. Bastian did with Buzz and Doris.